Can begin now. First, I would like to welcome you all and thank everyone for coming and joining this meeting and spending your valuable time behind this conference. We started this kind of uh, online seminar last year. In that seminar, I was the keynote speaker first time. So arranging this seminar was especially initiated by our higher study research group. That means the ex-student of the Chittagong University from mathematics. Some of our students are pursuing their PhD in Europe, America, and other country in the world. So they are interested to encourage the graduate student, fresh graduate student, uh, to do their higher study in abroad and introduce the application of mathematics, especially computational mathematics, to the graduate student. So this is the reason actually we arranging the seminar. So our intention to organize the seminar monthly.
So I like to mention, as mentioning that there are a lot of application in medical field. When we do the X-ray, CT scan, MRI, there are a lot of things go behind when you do the development, the mathematics, how to find the pattern, image recognition. Then we do also in the supply chain and logistics area, a lot of linear programming, integer programming, nonlinear programming, all those involved. Then when we do the artificial intelligence, neural network, genetic algorithm, then simulated annealing, so all will be in the mathematical involvement. Then when we do the failure prediction forecasting, so that's how we can collect the data and do all the prediction model, optimization model, and find the failure prediction or the forecasting using mathematics. Then this is kind of mentioning the prognostic and diagnostic. We can do all using mathematical model, and very difficult to do real life optimization without mathematical modeling. That's why mathematical model is so critical for us. Then when we do the FEA, CFD, CAT, CAM, all behind the scene, all computer programming, that when you have the coordinate system, how do you make all the logic, relationship database, and it will be using the mathematics model. Then you could see here I am bringing one aerospace aerodynamics. When you do all kind of modeling, and that's you test it before making any parts. So all the computational work. And this is one example from our student, like for the engine. So you can develop the design of experiment, how we can improve the engine production. Then there are many tools. You can see industrial engineering, industrial math, and computational math, all are related. You can see statistic, heuristic, response surface methodology, stochastic, ARMA, all with DOE. So we teach theory of constraint. We teach all those things part of industrial engineering. There are a lot of similarities that IM society can get involved with those areas. So here I'm not going through the IM society vision, mission, and values. You can see from our website. So what I'd like to mention that part of IM society, we have the global council member from 5 continents, and we organize many conferences. We do annual conferences, North America, Europe. You can see annual conference we started in 2010, Bangladesh for IM society. And then we are moving forward. Then we have the African conference, South America. We are starting India conference. We had our global engineering education conference, and we'll be having Asia Pacific conference. You can see every year we are having 4 or 5 events in globally. So we have various student chapter. So you could see we have close to 140 students. Will help students develop their portfolio. While they are studying, they do the presentation, they attend meetings, seminar, they join the different committee. So that's why they can develop. So when they graduate, they are not just getting a certificate with the GPA, they are getting other communication, team building skill, and that's are necessary to get a job. So we would like to have all students should have excellent academic record, and beside that, they should have other portfolio. When they graduate, they can compete with other students and they can meet the industry challenges. So we do different kind of award, like we have the award fellows, and this is upcoming conferences you could see in Singapore, in Brazil, we have in Rome, then we have in India, and then Mexico in North America conference. So I like to welcome everybody for this webinar.
Honorable chief guest, a special guest, and our keynote speaker, Dr. Mujib Chowdhury, University of Texas, USA, and all present audience. Good evening. Uh, it's my great pleasure to present as a special guest in this webinar of a lecture series on computational science, uh, organized by Higher Studies Mathematics Group. And I think this is the second one of a new series of academic endeavor exploring how we use mathematics in computational science. And I would like to special thanks to Dr. Jalal to organize such a webinar. And I think, I hope that everyone will enjoy this webinar. Thank you very much.
Like to thank the organizer, especially the Higher Studies Committee of Chicago University. And actually, this program is jointly organized by the Industrial and Computational Mathematics Research Group and IOM Society, Chicago University chapter. Actually, IOM Society is a very well-known, internationally recognized international society, and Bangladesh have also a professional chapter. And we are actually the founder of the Bangladesh chapter of IOM Society. So Dr. Ahad Ali, actually the executive director of the society, leading the society internationally. So the society is actually now is very well known in the all over the world. So I would like to thank Dr. Jalal because he is the faculty advisor of Chittagong University, IM Society and chapter. And this program actually brings a lot of hopes and a great attraction for the professor, actually for the students who wants to start their life, start their study in biomathematics or computational mathematics. Today, actually, due to the limited time, I would not present here actually my research. Just I would like to say some thing about the computational mathematics, because after the development of the computational techniques, mathematics have been very well known tool in the real life application of mathematics. So mathematics everywhere, we cannot think not a single time, not a single days, not a single moment without mathematics. And in that case, computational mathematics fuels this situation because it deals with the real life application. So today's, I think that today's lecture will be a very attractive also in pattern recognition. And my research area is actually modeling in biological system, modeling in biomedicine, and modeling in ecology. So every real life application actually it dominates mathematics, and in that case, computational application gives the real theme, gives the real interest to study in such a fantastic area. So I would like to request the young researcher, our students, our young faculties, and those students who would like to take their higher study in computational mathematics. So you can study, you can see several papers in my website. You can search my website also. So I think it will be very interesting and to work in this area. And I welcome all the young researchers working in this computational area, computational mathematics. So mathematics, how can mathematics be applied in real life application in situation. So this is the fact the computational and mathematics did. So I cannot spend more time. Just I can say this webinar will bring a new dimension, a new horizon for the young researcher, and hope everybody will enjoy this webinar.
Honorable Chief Guest, Professor Donald Reimer, and Dean of Science, Professor Nasim Hassan, and distinguished guest of this webinar, Dr. Lau, Professor Haider Ali Bishas, Dr. Ahad Ali, and keynote speaker, Dr. Mujib Chowdhury, and moderator of this session, Professor Jalal Ahmed. Ladies and gentlemen, I would like to offer warm congratulations to all. Computational science is a multidisciplinary subject which is becoming a ubiquitous tool in science and engineering. Along with gradual theoretical and experimental advancement of science, human brain is unable to process this theoretical modeling or experimental use data in a meaningful way. That is why without computational science, the truth of nature cannot further be analyzed in a fruitful way. Further scientific achievements will mainly be dependent on data analysis efficiency. Nowadays, non-scientific disciplines such as social and business activities are becoming model dependent. Human race first observed black hole image in 2019 from mathematical concept to a physical object by analyzing 4.5 petabytes astronomical data from EHT. For example, if one captures 4,000 typical cell phone photos per day for 200 years, it will be equivalent to 1 petabyte. So without data science, it is impossible to extract truth from these enormous data. CERN archived 200 petabytes of data permanently in its tape up to June 2017. It's a huge amount of data. And without uh, any data science, it is impossible to extract any decision from those data. It is very much essential to establish a data analysis center at the University of Chittagong, and we urge to our Honorable Vice Chancellor for taking initiative for this regard. I'd like to thank Industrial and Computational Mathematics Research Group, ICM, Department of Mathematics, University of Chittagong for arranging this wonderful webinar to extend our knowledge on this discipline and to share our knowledge to everyone. And I wish the ultimate success of this webinar. Thank you all. Thank you.
Hi, everyone. Thanks for inviting me and coming to Mujib's talk. I just want to say that he is like my former student, current postdoc. He did a very nice thing for his PhD work about image processing. And as you can see that right now, there's a lot of applications that involves mathematicians. And there's a lot of data, so that's why we call it big data challenges. But sometimes there's another scenario that we only have limited data. For example, in medical, the CT, we cannot scan patient too many times to have radiation overdose. So actually the problem I have been working on is mostly the small data. So we don't have enough information. So we need to impose some conditions, restraints, so that we can guide our mathematical model to find a preferred solution. And then I want to say that students may have some a lot of mathematical courses like algebra, linear algebra, calculus, but sometimes they don't know how to use those tools to apply technical problems in real world. So I appreciate if like for future we have some collaborations internationally and from school to industry. That would be a very good things to see in the future. Yeah, I think hopefully you will enjoy Mujib's talk. Yeah, that's all.
Thank you very much for this opportunity. Really appreciate the opportunity to be here to share with you a very interesting topic, the relationship between innovation and the entrepreneurial mindset. I want to talk a little bit about the mindset of the entrepreneur. And in listening to the prior presentations, it's kind of interesting for me because this is really not my space. The area that I focus on is creativity, innovation, innovative thinking. My research has been primarily on the entrepreneurial child and the thinking process of entrepreneurs. In this presentation, we're going to talk a little bit about the whole thinking process and really what that means. The entrepreneurial mindset is really able to assess the bigger picture, allowing them to recognize opportunities, evaluate markets, and learn from their mistakes. They're capable of more than just solving a technical problem. They're constantly looking for unexpected ways to create value. We're going to talk more about creating value in a few moments. I kind of define entrepreneurship as a compelling force within an individual that is driven by the recognition of an opportunity and a desire to create an enterprise. So the mindset of the entrepreneur, from an engineering perspective, consists of three key elements. Curiosity, really to demonstrate constant curiosity about our changing world and to be able to explore countering views of accepted solutions, and to be able to connect, to integrate information from many sources to gain insight, to assess and manage risk. Risk is an entire topic that I spend quite a bit of time talking about in my classes to the students. And of course, most important of all is the ability to create value. For engineering, discipline is all about creating value, identifying unexpected opportunities to create extraordinary value, and to persist through and learn from failure. Very important ingredient, learning from failure. This further expands the curiosity, connections, and creating value elements of the entrepreneurial mindset. And each of these really addresses some very interesting perspective from the entrepreneurial viewpoint. And you'll see in the first on your left, how important is empathy? Empathy, thinking about the voice of the customer and working with customers and listening to the customer. These are many, many experiences. And of course, in connections, we think about the outcome. What are the outcomes driven by innovation methods and tools? We'll talk more about these tools in just a few moments. But the essence of creating value is to engage real customers, to get out of the laboratory and to design solutions, real solutions based on customer needs, welcoming customer feedback and learning from this feedback. We can see that creating value is all about innovative solutions that are most meaningful and creating extraordinary value. And I want to stress extraordinary value. The more extraordinary value you create, the more the customer is willing to pay for that value. Students must be champions of value creation. As educators, we must train students to persistently anticipate and meet the needs of a changing world. So one of the tools that I use in my classroom is painstorming, not brainstorming, heuristics, the Gordon method, the scientific method, the focus groups, but painstorming. So what is it? Well, painstorming is the process of uncovering pain points to drive through breakthrough innovation. Instead of jumping to solutions, painstorming uncovers the fundamental drivers of new opportunities. So in a sense, painstorming is an opportunity, recognition, and validation tool. So what pains you? Well, on the screen, you see many different pains, whether it's a glitch, a difficulty, a complication, a frustration, a hazard, a fault, a trouble, whatever that might be. These pains are faced by all of us. We utilize these pains to identify the pain causer and, of course, the solution, which is the pain reliever. So I do not know how many of you have 2-year-olds. If you have, you'll know the experience of the, well, I hear some background music. So we think about shoes and how do we solve this problem? Well, here's a product that was developed and commercialized. So you can see in placing the left and the right shoe, how difficult that might be for a 2-year-old. And this was the solution. Here is a use of gravity, as you can see, for this bookcase. Again, an innovative solution. Here's a traditional ketchup bottle, glass ketchup bottle on your left. And here is the packaging solution, again, using gravity. What was the pain? Well, getting the ketchup out of the bottle and maybe relieving the ketchup onto your food, and it comes out much too quickly. So this plastic container upside down using gravity solved or relieved the pain reliever. For years, I'm sure there's somebody in the audience that remember when luggage did not have wheels. Well, when did this happen? Why did this happen? Well, it happened in the early 70s when a man by the name of Sato actually brought together wheels and luggage. Again, this was a breakthrough. This was not an enhancement. And again, there are many reasons, there are many societal reasons why this occurred. And I'm sure there are a few people in the audience that do remember having wheels were not included in luggage. When I talk about this subject in my class, of course, everyone in the class cannot ever recall having a piece of luggage without wheels. This is an example of where an enhancement where luggage actually includes a scale. This is I would say, maybe an enhancement. Some would call it a breakthrough of the development of the Kerr coffee machine. So here's an example of painstorming and societal painstorming. Can you imagine hauling water? And maybe this is still true today in many parts of the world. I'm sure it is. So sometimes, I guess, in society, we turn on a faucet and water comes out and it's all wonderful. And hopefully that water is clean and usable. And that's so what was the solution? This was very painful, obviously. Well, the solution was something called the Q drum. Q drum was a very interesting, very simple, no moving parts. So you can see how the problem was solved. We talk about value proposition, probably one of the most interesting books. I've used this in my classroom for years, and that is Osterwald and Pignow's book, Value Proposition Design. I really urge you to think about utilizing this material. It is very easy, simple. It can be applied And it really discusses the relationship between the customer and the value proposition. And how do you design a value proposition that really is meaningful to the customer? Now, when we think about the world of innovation, there are many ways to think about it. But I always think about the Model T Ford. And I suppose if Henry Ford was with us today, and we were discussing with him, look, let's create this Model T. And if Henry Ford asked the customer, what would you like? Would you like this type of vehicle? Many of the customers would say, look, just bring me a faster horse. Everything would be wonderful if we just had a faster horse rather than this contraption called a Model T Ford that was built just a few miles from where I am sitting. Innovation is a very interesting topic. When you look at all of the companies here that are represented, whether it's Kodak, BlackBerry, Polaroid, what do they all have in common? Well, of course, all of them are either no longer existing or greatly reduced in their market penetration. They were not innovative thinkers. And I think the most interesting thing about the Kodak slide is when a couple of engineers came to their supervisor and said to them, guess what? Our customers will no longer need film. We've found a way to eliminate film, and that's called the digital chip. When did that happen? It happened in Rochester, New York in the mid-70s. Did Kodak do anything about it? Of course not. They did not want to destroy their cash cow business, film. And they also had acquired a company called Eastman, and that was the chemical company that they eventually used to develop their film. Developing film was no longer necessary. When I brought a camera with film to my classroom to discuss how systems evolve, it was amazing to listen to the students and their feedback about innovation. And the question becomes, when you think about innovation, I'll plant the seed with you. Is innovation a science? Can it be taught? If so, how? Are we teaching our students to be more innovative? Why are some engineers more innovative than others? So when we think about innovation, we think about these many, many topics, mathematics, of course, which we're talking about, computational mathematics, applied mathematics, statistics. All of these apply when we think about innovative thinking. As I listen to all of you, I think about opportunities. I think about opportunities using computational science, mathematical modeling. And in working with Dr. Ali, often I hear about the value, the importance of computational modeling, optimization. So important. Think about the potential for innovative idea modeling in gaming, optimization and failure prediction, statistical process improvement, and supply chain and logistics, timing and performance. Dr. Ali talked about medical applications as well, FED, CFD, simulation, computation, validation, all very important. So one of the books that I've used for many years is the Business Model Generation, again by Osterwilder. This is a diagram of a business model canvas. In one of my classes, we use this document extensively. It is a validation tool to help the learner understand the validation process once you come up with an idea. And at the center, you can see is the value proposition. What problems need to be solved and what product does it best. And of course, the relationship between value proposition and customer segments. Whom or who are you creating value for? And that is a very, very important important idea when we think about the 9 components of the business model canvas. So when we think about commercialization, we can think about these ideas: reducing the length of waiting time in a theme park, developing prototypes for cell phone car adapter market, and of course, designing clothing warehouse using computational or computer simulations and developing innovative prediction models for industry. So examples of the applications and commercialization is to create a quality assurance program for a national restaurant chain, or prevent workers' injuries with ergonomic intervention programs, or making customer service more efficient in an electronics company, or launching material handling system for a new automobile company, and developing conceptual layout of a dockyard. And certainly in Bangladesh at this time, the emerging industry of shipbuilding has been brought to my attention. And I think here's some interesting work that could be done in that regard. This industry will continue to evolve and continue to grow. And I'm very, very excited, and you should, as a country, I'm sure you're very proud of this emerging industry, as well as others in Bangladesh, creating jobs and economic empowerment. So when we think about the innovation process, we must think about prior art. Prior art is the possibility that someone else in the world has actually created this idea, that it exists, that there is a patent. The United States Patent and Trademark you can use the site to determine whether that there is a prior art, uspto.gov. You can Google alternate sources of intellectual properties as well. You can evaluate the extent of the patent that has been issued and the claims that are stated in the document. Is the existing patent close and or similar to your idea? If so, what are the next steps? And of course, if there are innovation, incubation environments within the university, within the country, utilize those, develop the sources that you have to fine tune your idea and prepare it for launching. Thank you very much for your time, for the opportunity to share my thoughts with you.
Before starting my talk, that's a quick announcement for the students who are attending today. If you have any question and if you hesitate to ask in English, you are most welcome to speak in Bangla. We can interpret it for you. Okay, let me start my talk. Today, I'll be talking about some mathematical models I have developed during my PhD work for image denoising and deconvolution, together with my advisor, Dr. Ifei Lo. I think she just left. So this is the outline of my talk today. In the overview, I'll be talking about some the definition of the image noise, why image blur occur, and what is the image regularization, and what is a fractional derivative, what is FOTB and data fitting term for image denoising, and so on. Then I'll move to the first model, image denoising model. Then I'll be talking about two of my deconvolution model, blind and non-blind image deconvolution. Finally, I'll conclude my talk today. So what is image? Image is a matrix. We can represent image as a matrix. Each element of the matrix can be represented as an intensity value of the matrix. So what is the noise? Noise means image noise is a random variation of the brightness. So random noise is characterized by intensity and color fluctuation above and below the intensity value for intensity value. And this image, this noise can be produced by image sensor or digital camera. And the source, I mean, if we consider the photon count devices like the medical imaging device, X-ray, CT, or any astronomical devices. So the sources from there emits the number of photons which are detected by a detector. So the image intensity is given by the number of detected particles in a given time interval. So these sources are having random fluctuation of the photons. So we have some, the image has a special and temporal randomness. This noise is called the Poisson noise. There are different kinds of noise occur on the images, but today I'll be talking about only Poisson noise, which can be found in the photon count devices. And also another inevitable artifacts on the images we found that's called the blur, image blur. The blurring can be introduced by optical system. It can also be introduced by improperly focused lens, relative motion between the camera and source. And blurring is a form of bandwidth bandwidth reduction of an image owing to imperfect the image formation process. So if you see the second image, the first image is the original one, and the second image is corrupted by the noise, and the third image is corrupted by noise as well as the blur. So the first model I developed to recover the image, the original image from the second image, noise image, and then second and third model, blind and non-blind deconvolution, I developed to recover the image from this noisy blurry image. Okay, now let's talk about the image regularization. Before that, let me talk about the regularization. What is regularization? Why do we use the regularization? So regularization is the process of adding information in order to solve an ill-posed problem or to prevent the overfitting. So it helps to shrink the solution space. Ill-posedness means what? Ill-posedness means if the system of equations doesn't have any solution or it has infinitely many solutions, then we call it ill-posed problem. So from infinitely many solutions, we can shrink the solution space using the regularization. And also this regularization technique widely used in machine learning and deep learning method to minimize the loss function or hinge function. And recovering image from this corrupted image or noisy blurry image is called an inverse problem. And due to the noise and this blur, the recovery or reconstruction of image problem becomes highly ill-posed. And so we need to incorporate a regularization. So total variation is the most popular regularization widely used in image processing, but it causes some staircasing artifacts, though it works well for piecewise smooth image. So to remove the staircasing artifact and speckle artifacts, we use the fractional order total variation. Fractional order total variation can remove the noise, as well as it can also remove the staircasing artifact and speckle artifacts, and it can preserve the edges of the images. Moreover, we are considering the Poisson noise. So to deal with the Poisson noise, we need to consider the log likelihood function. So the log likelihood function makes the problem nonlinear. So it is very difficult to solve a nonlinear ill-posed problem. That's we are dealing with in this project. TB means the total variation with order of the derivative is 1. Fractional order TB means with the derivative of order is a fraction. Order could be a fraction like 0.5 or 1.5, something like that. So before defining this fractional order TB, let's define the fractional calculus by studying an example. This example was derived by Lacroix 200 years ago. They simply derived the fractional derivative of this simple power function ut equal to t to the m, where m is any real number. Now, if m and n, they are positive integer, then the nth order derivative of this simple function t to the m is given by this formula. But in the formula m, in the given function m is any real number. You know, the factorial, this is only defined for the integer number, not for the fraction. So what do? There is a function called gamma function. We can use this gamma function. The relation between gamma function and factorial is factorial m equal to gamma m plus 1. So we can replace this factorial m by gamma m plus 1, and we get the nth order derivative of this simple power function ut equal to t to the m, where m is any fraction or real number. So this derivative we can extend to a fractional order derivative by replacing n by alpha, where alpha is any fraction, and we also replace m by factorial gamma m plus 1. So this is the alpha order or fractional order derivative of the given function t to the m. So for example, if you want to take the half order derivative of t, you know the first order derivative of t is 1. How about the half order derivative? So to find the half order derivative, what are you gonna do? You simply plug alpha equal to 1 half, and since the exponent of t is 1, exponent of t is 1. So m, you flag m equal to 1. So after flagging alpha equal to 1/2 and t equal to m equal to 1, then you get the half order derivative of t is 2 over radical pi times t to the 1/2. Now, if you take further half order derivative of this result, then you get 1. So, the half order derivative of t is 1. That means the first order derivative is 1. I hope you get any intuition about the fractional calculus from this example. Now let's go to the definition. The definition of the fractional derivative is not unified yet. There are many definitions in the literature. So GL, they derived the fractional derivative in 1867 and 1868 separately. So they derived this definition from the fundamental definition of the derivative. So the fundamental definition of the derivative for nth order derivative of the function is given by this formula, where Cnk is given by this factorial n divided by factorial k times n minus k factorial. So that simply extend this nth order derivative to fractional order derivative by replacing n by alpha. Alpha is a fraction, and they also use the gamma function to replace the factorial, and they replace this summation nth sum to infinite sum. Okay, now for the implementation, we need to truncate the infinite sum to finite sum. Otherwise, we cannot implement in computer program. Or k versus c for this term, k versus c, and we see c is decreasing gradually, and at k equal to 15, c goes to approximately 1e minus 4, which is close to 0. So we can truncate at k equal to 15. We may have some truncation error, but it is negligible. We choose h equal to 1 number of panel and truncate it to up to k. Then it leads to this formula, which is the finite difference scheme for the fractional order derivative. Okay, now we discretize the domain omega. Omega is the domain for the image by this, and image can be represented as a matrix, as I mentioned earlier, and each element or intensity can be represented as a UI. Fractional order gradient of U can be defined as by equation 5, where d1 indicates that it is the derivative along x-axis, and d2 means that it is the derivative of y-axis. Then let's define the fractional order derivative by equation 7, where the first one, d1 is the first order derivative, is the second order derivative, and alpha order derivative. And if we plug alpha equal to 1, then this FOTB reduces to 1. As I mentioned earlier, TB is a special case of FOTB, fractional order total variation. And the derivative, it works, it acts as an operator like a matrix, and the divergent is an adjoint operator of the gradient. So we can use this relation between the divergence and gradient during our experiment. Okay, now data fitting term. The most commonly used method for solving this kind of system in regularized least square method. The choice of this data fitting term depends on the noise statistics. The first term for the Gaussian noise, if we consider the Gaussian noise, then in the literature is considered this least square data fitting term tu minus f, where t is a linear operator, or we can say for our case degraded operator. It actually degrade the image. So for the denoising case, we consider t as a identity matrix. For the deblurring case, deblurring image, we consider t as a convolution matrix. For medical image reconstruction, for example, the CT reconstruction or PET reconstruction, we consider t as a projection matrix. Okay, so you see, I mentioned U as a matrix, U is an image as a matrix. So, but for this calculation, we stretch U as a vector. So you can think about this is a matrix vector multiplication, and F is also vector, so we can get the dimension match. But for the Poisson noise, as we are considering the Poisson noise, F follows Poisson distribution. One common approach for image restoration under Poisson noise is based on the modification of this data fidelity or data fitting term, the least square misfit, to logarithmic concave form. So we replace this least square form to logarithmic form to deal with the Poisson noise. And here T is the linear operator, and 1 omega, which is the indicator function, which is equal to 1 on the image domain omega and 0 everywhere else. And we can solve this function h of u using the EM algorithm, expectation maximization algorithm, this widely used algorithm. And then the Lagrangian is given by equation 11 and 12, where T star is the adjoint. For our case, it's a simply transpose of the matrix, and lambda is the Lagrangian multiplier, and this dot circle means it's an element-wise multiplication. Then we get this updating is equation number 13, and using the equation number 13, we get our function. This h function is decreasing gradually. Then let me move to my first model, fractional order total variation based Poisson denoising model. In this model, we proposed a regularization FOTB plus a data fitting term. So the first term is the regularization, and the second term is the data fitting term, and beta is the balancing parameters for parameter for these two terms. And by this theorem 1, we can show our model. Our model has unique solution on a finite dimensional subspace. This paper has been published in Inverse Problem and Imaging in early last year. And to solve this model, we propose ADMM, alternating direction method of multipliers. So to reformulate our model 14, we introduce another variable z. So z equal to nabla alpha u. Why do we introduce this new variable? Because if we introduce this new variable, then we can get closed form solution for all the variables u, z, u, and z. So the augmented Lagrangian for this corresponding problem 15 objective function is given by this, where this term is the Lagrangian which imposes the constraint. And the last term we added, this is called augmented term. This augmented term makes the problem stable and convex, so we can get the unique solution. Then this is the ADMM scheme. In the you see u involves a u involves a logarithm, so it's a non-linear problem, so we can get the approximate solution for u. And for z, it has a L1 norm. So to solve the L1 norm, there is a method called shrinkage operator. Using the shrinkage operator, we can get the closed form solution for z. And for lambda is updated by the ADMM framework. So you see, whenever we solve for u, we consider rest of them as a constant. And when we solve for z, we consider rest of them constant. So alternatingly, we are solving this problem. So that's why this is called alternating direction method of multipliers. Okay, so to quantify our result in the experiment, we use two quantifiers. One is peak signal to noise ratio (PSNR), and the second one is structural similarity index (SSIM). So the higher PSNR, the better recovery of the image. Same thing goes for SSIM. The higher SSIM, the better image. But the range for SSIM is 0 to 1. If it is close to 1, then the image is close to the original image. The recovered image is close to the original image. We started our experiment with a synthetic image. This synthetic image we created using this equation, x to the 0.8 plus y to the 0.8 on a mesh grid -50 to 50 times -50 to 50. So on this mesh grid, using this equation, we create the synthetic image. And the noise level for the Poisson noise, the noise level can be controlled by the peak intensity. So we scale the original image with a preset peak value. So before adding the Poisson noise. So for our case, we consider 3 peak values here in this work, peak equal to 55, 155, and 255. And you see the larger peak, for the larger peak value, the less noisy the observed image becomes. What I mean by that, if you look at this peak with 55 image, this is more noisier than this image with peak 255. If the image peak is lower, then image looks more noisy. And we apply our method into this peak 255 image to recover. When at alpha equal to 1, we get this image. This is the recovered image using our method with alpha equal to 1. So which is actually TB, total variation. So you notice here it has some staircasing artifact. And for 2.4, the image gets over smooth. But we are getting the optimal value at alpha equal to 1.8. But why? Why do we get this optimal value at 1.8? Poisson, they showed in a paper in SIAM imaging, if the image is reconstructed, the image is constructed by this equation, absolute value of x raised to the power r plus y to the r, then the optimal order occurs at r plus 1. Since we are considering r equal to 0.1, 0.8, so the optimal value for our case would be r alpha equal to r plus 1, which is 1.8. So we tune the parameter for alpha, we see we got the optimal value at 1.8. Then we move to some natural images, 5 natural images: cameraman, penguin, train, mandrill, barbara. These are widely used images in image processing literature. And we consider 3 peak value, 55, 155, and 255. And we compare with the state-of-the-art methods, NP tool, NLPCA, BM3D. So NP tool is a MATLAB toolbox for the non-negative image restoration with Newton projection method. It uses the TB, total variation technique. And NLPCA, this is also a MATLAB toolbox and is based on the idea of non-local patches together with PCA. I mean, principal component analysis for dealing with the Poisson noise. And BM3D, finally, it uses the Anscombe transformation. Using Anscombe transformation, BM3D transform the data from Poisson distribution to Gaussian distribution. Then it removes the Gaussian distribution. Then it takes the inverse Anscombe transformation. That's how it removes the Poisson noise. So here in this table, I bold for every test case, I bold the best result. So if we look at the result, most of the cases, our method dominating over the state-of-the-art method. Though for the Barbara, the image BM3D works well because BM3D work patch-based. But still, we can get improvement over TB for this NP tool. NP tool, we get significant improvement according to the PSNR and also according to the SSIM. Now let's look at some visual result. So this is the cameraman. If we look at this visual result, for the cameraman, it looks more sharper than everything else, BM3D. But if you look at the zooming part, we zoom this head of the tower. So if you look at the BM3D result, the head of the tower, it cannot preserve the edges. Though it looks sharp, the image looks sharp, it waved the edges of the tower. Now, if you look at our result, our method can preserve the edges as well as it can remove the noise. Now let's look at another visual example for the mandrill. For the mandrill, same thing goes here. For the BM3D, looks the image sharper, but it cannot preserve the edges. It cannot preserve the edges as we can preserve the edges for this mandrill in the zooming part. You can look. Okay, now let me move to the second work. So recorded images are typically blurred due to the physical mechanism of an imaging device, as I mentioned earlier. So the blurring process can be characterized as a point spread function, PSF, or kernel in other words. So it's a convolution of this PSF, the kernel, and the image. Then we get the blurry, noisy image. Deconvolution is the process of recovering true image from the observed image. And there are two types of deconvolution. One is called non-blind and the other one is called blind. Non-blind means you are given the corrupted image and the kernel or PSF. So, but in real scenario, you are given only the corrupted image or noisy blurry image. You don't know anything about the information about the PSF or kernel. So without knowing the kernel, any information about the kernel, you need to retrieve or recover the image. That's why this is called blind deconvolution. And blind deconvolution is highly ill-posed problem. And there is infinitely many solutions. For example, no blur solution. No blur solution means what? No blur solution means you are solving here simultaneously U and H. So you are getting H as a delta function, yeah, and U is a blurry image. So if you multiply, I mean, if you convolute to each other, you get F. So it could be a solution. Actually, you are not looking for the blurry image. You are looking for the sharp image. So it may get stuck into this no blur solution. This is the first model for image deconvolution. The first term is as before, the regularization. The second term is the data fitting term. Here, if you notice here, we introduce a blurring kernel edge. In the previous method, we consider for denoising case, the T operator equal to I. That's why we didn't put I there. But here we are considering the blurring case, so we need to incorporate the kernel. So that T is replacing by H kernel. H is the kernel, and this is the convolution operator. The circle star, this is the convolution operator. And to implement this convolution, we use the FFT, which makes the problem faster. So again, to solve this problem, we propose the ADMM. So here we introduce two auxiliary variables, Z and G. Z equal to nabla alpha and G equal to H convolution U. So this is the augmented Lagrangian function, and the lambda 1, this term imposes the first constraint, and this lambda 2 imposes the second constraint. And these two are the continuation term or augmented term. These two terms makes the problem stable, and it makes the problem convex. So we can get the unique solution. We implement our method into 4 images: cameraman, galaxy, phantom, and shape, with 4 peak level. P equal to 55 for P over 2, P over 5, and so on. And here also we compare with a state-of-the-art method, RLTB. RLTB is a Richardson Lucy TB, which is a very popular method in statistics and this kind of computation. And the NPTOL and BM3D I mentioned in the denoising case. Now we are using in the blurring case. In this case, we brought the best result. So if we look at the result, most of the cases our method dominating. Now, if we look at this cameraman for, let's say, P over 2, according to the PSNR, according to the SSIM, our method both are same, but according to PSNR, BM3D is slightly winner, slightly better than us. Now let's look at the visual result. So this is the BM3D, which PSNR 24.20. 20, and for our case 24.15. But if you look at the visual result for suppose for the zooming part, this camera, it has some ringing artifact. Not only zooming part is, if you look at around the images, there are many ringing artifacts. But in our case, there is no ringing artifacts. So FOTB can remove the ringing artifacts as well as the speckle artifact. Now let's look at another image. This is actually a synthetic image, and it's a piecewise smooth image. So BM3D works fetch based. It looks for the similar batch. Since this image doesn't have any similar batch, BM3D cannot get a good result. And NP tool, this is based on TB. Since it's based on TB, it should have some good result. I think the model, their method may have some problem. That's why we are getting the bad result for this lower peak. The peak is only 25.5. For the blind deconvolution, it's the same model we are considering, but this case we minimize this model over both U and H. Simultaneously, we need to recover U and H. So the boundary condition plays an important role in the success of blind deconvolution. To suppress the ringing artifacts around the boundaries, we crop the data in such a way that the boundary condition doesn't have any effect on this objective function. So we only consider the crop version of the image. So you notice here, that's why we denote F by F bar. F bar means we are considering only the crop version. You know, the blind deconvolution is significantly more challenging than non-blind deconvolution, as it requires to estimate both simultaneously U and H. So the joint estimation of H and U often leads to no blur solution, as I mentioned earlier. So how do we avoid this kind of problem? So this problem can be avoided by sequentially projecting the kernel onto a feasible set of non-negative and sum to one solution. Then we can shrink the solution space. So to minimize the problem with respect to H, we consider this convolution as a matrix vector multiplication, since it's a symmetric U and H. So we can use the EM algorithm I mentioned earlier. And by this equation, we are projecting our solution into the solution space, feasible set of space for non-negative and sum to one solution to avoid the ambiguity and scale ambiguity. Okay, before presenting the result for blind deconvolution, let's compare our two proposed methods, non-blind and blind. So if you look at these two results, non-blind and blind, according to the SSIM, they are almost same. They are same. But according to the PSNR, the PSNR for blind deconvolution is close to non-blind. And if we look at the visual result, they are almost same. So actually, we can successfully retrieve the image in the blind deconvolution as well, though we don't have the PSF or kernel is given. Okay, so we apply our method, the blind deconvolution, into three images. Shape is a which is a synthetic image, then a spine is a medical image, and then satellite, which is astronomical image. And for complicated image with more features, the blind deconvolution cannot handle as much noise as non-blind can. So that's how we increase the number of the peak value here, 1E3, which means 1000. And we compare with the method, existing method, EM algorithm. This is our own implementation. The MATLAB has its building function, which is even worse than this method. And if we look at the result, for all cases, we have a significant improvement, more than 10 PSNR, for some cases, we got the improvement. And also according to the SSIM, we got significant improvement for this blind deconvolution. Now let's look at a visual result. There are different kinds of kernel, like motion kernel or Gaussian kernel. So the first row here, we use the Gaussian kernel. The second, we use the motion kernel. So this is the original image and this is the original kernel. They are convoluting to each other. Then we get this input image. And using the EM algorithm, we can retrieve this image and also we can recover this kernel. And this is our result. So if you look at the result for the kernel, EM can the kernel recovered by EM, which is better than the kernel we recovered. But if you look at the image, according to the image recovery, our one is way better than EM algorithm. And for the motion blur in the bottom row, so this is the input image. So this is the output or recovered image using the EM algorithm. You see EM algorithm, it's almost recovered the kernel. But if you look at the image, our image is way better than the EM method. And also if you look at the numerical result, the PSNR and as well as the SSIM, so we get the better recovery. So now I'm going to conclude my talk today. So we proposed here two types of method or models, one for denoising, image denoising, and two for image deconvolution, blind and non-blind deconvolution based on the fractional or total variation. And we showed our method have the great potentials in recovering the piecewise images under the Poisson noise. And currently we are working on L1/L2 regularized based method for CT image reconstruction. CT image means kind of medical imaging. And our plan is to develop some deep learning method, because for the image deconvolution, conventional method is still superior than the learning based method. So our plan is to investigate some deep learning method in this regard. That's all. Thank you, everyone. Any question?
Thank you, Dr. Mujibur Rahman, for your nice presentation. Do you have any question? You can ask any question. As Dr. Mujib proposed, you can ask in Bengali even.
Dr. Mujib, so I saw you use the synthetic photo or pictures for the benchmarking. Do you use any photos from the real world, that means any CT scan data, and then validate with the professionals? That
Can you open you?
Thank you for those. What I presented today is not the medical imaging. It's only for the natural imaging, image denoising and deconvolution. Same kind of technique we can implement in the CT reconstruction. But I already work on it during my PhD work. So mostly we work on the synthetic data for CT reconstruction. And what we are working now is L1/L2. This work also almost done for the synthetic data. Now we are waiting for the real data to work on it. We are collaborating with UC Davis, University of California Davis, also collaborating with UT Southwestern. We are waiting for the data from them. Once we get the data, then we can test our model using the real world data. Thank you.
Another question, sorry. Thank you. Thanks for answering. So though this is not the present work you have finished or presenting here, is the future that you talked about. So you talked about the deep learning process of a deep learning algorithm. So what kind of deep learning you were thinking? Or because this is kind of trial and error most of the time, are you considering to create another level of reinforcement learning above your deep learning algorithm?
Thank you, Ferdows. It's a good question, but we are not there yet to answer your question, because we are still thinking and finishing this work, L1 over L2 regularized based. Once it's finished, and we are reading the literature. From the literature, we found still the conventional method is superior, but we don't know why the learning based method is not working. That is the reason we are getting motivated to work on it, to investigate those fields.
Okay. Any more
Thanks.
question from audience? If no, so I have a couple of questions.
Sure.
So actually, fractional derivative, he is working. It is a very interesting thing in the imaging process. So we know, if I understand correctly, we know the integer type derivative. We learn from the intermediate level, right? But the
Yes.
situation of any dynamical system may occur in fractional time, right? Suppose if you want to calculate the differentiation, changing the rate of traveling any particle, usually we calculate 1 second, 2 second, 3 second, 1 minute, 2 minute, right? But if it happen 1.5 minutes, then what will happen, right? This kind of dynamical system actually very useful to use the fractional derivative. Even in CFD application, it is very important to explain more accurately the physical system, right? So now my question: are you using Gaussian or Poisson noise to eliminate blurry of image?
I'm considering the Poisson noise. That's why we are considering the log likelihood function. So our method that's why becomes a non-linear. So if we consider Gaussian, it's very easy because it's a linear problem.
Yeah. Okay. So could you go back to slide number 13, please?
13. Okay. This is the 13, right?
13.
Okay. Yes.
Okay. So you are using alternative direction method of multiplier, and in this case you are using a Lagrangian functional, right? So what is the
Yes.
benefit? What is the benefit? What is the numerical benefit of this Lagrangian approach, Lagrangian function?
Well,
I mean numerical benefit.
If we use this method, then we can get the if we use the classical levels. But if you use this ADMM and this Lagrangian, then you can decouple the variables using the ADMM. That's why we use this.
Okay, thank you.
And if I understand your question correctly,
okay,
why do we
okay.
use
Yeah,
the
I
ADM?
understand. Yeah,
Sorry,
good
the
question.
augmented
Good answer.
Lagrangian.
Good answer.
The augmented
Okay.
Lagrangian, we are imposing. Yeah. Okay.
Okay. So now my next question: how are you controlling ill-post problem here?
Well, thank you. So as I mentioned earlier, so to control the ill-post problem, we are using the regularization. Regularization is kind of a prior knowledge you are adding with the objective function. So if you add some prior knowledge with the objective function, then you can shrink the solution space. That's how you deal with the ill-post problem in image processing.
Thank you again. Have a good night.